Greetings and welcome to the O-Level Revision series. This is part 3 of the chapter on polynomials, and in this video, we'll be learning about the remainder theorem and polynomial identities. The success criteria for this video would be for students to be able to solve for unknowns in a given polynomial identity, as well as to apply the remainder theorem. Now a quick recap. In the previous video, we've learned about the polynomial long division algorithm. We have also learned how we can express the dividend as the product of the divisor times the quotient plus a remainder. But to be really precise, these two expressions are not just merely equal, they are actually equivalent, and we use this three lines to represent equivalence. What equivalence means is that these two expressions are true for all values of x. You cannot possibly solve for x. X can be any number you like. For example, we can substitute x to be pi, and if we compute this number, we'll get this long decimal 9.026818, so on. And if I substitute it into the right hand side, pi minus 3 times 2 pi squared minus 3 pi plus 4 plus 7, and I input this in a computer, I will get the same value. So these two expressions are identical. They give you the same result for all values of x, and we call this a polynomial identity. So let's go straight to an exercise. Express negative 4x squared plus 12x plus 1 in the form of a bracket x minus h squared plus k. Pause the video here and give this a good try. Let's recall how we complete a square. First, we'll need to factorize out the a, which is negative 4, from the x and the x squared terms. So that will leave behind x squared minus 3x. We'll leave the constant 1 alone for now. To complete the square, we need to add half of the new b term squared and subtract it again. So something like this. So you can see the negative 3, we'll have to halve that, then we square it and we add it. But we have to subtract it to ensure that the expression is still equivalent to the previous form. Next, we look at the first three terms. This is a perfect square, so we can factorize this. So we'll get x minus 3 over 2 squared. The negative 3 over 2 squared, we can simplify this. This will become 9 over 4. Next, we will distribute the negative 4. This will give us negative 4 times the perfect square, which is x minus 3 over 2 squared, plus a 9. So negative 4 times negative 9 over 4 is 9. And we have to still add the 1 to get positive 10. So we have completed the square. We can see that a equals to negative 4, h is 3 over 2, and k is 10. But why on earth are we completing the square in this polynomial chapter? Well, it turns out there is another way to do this using polynomial identities. Since both the forms are equivalent, we have an identity, meaning that if we expand, we get ax squared minus 2ahx plus ah squared plus k on the right hand side. These two forms are equivalent, so the coefficients are equal. So we can compare the coefficients. So let's compare the x squared terms first. Negative 4 is equals to a. Well, we've solved a. If we look at the x terms, the coefficient 12 is equals to negative 2ah. Well, the constant term on the left side is 1, and the right side is ah squared plus k, so they are equal. Since we know that a is negative 4, I can solve for h to be 3 over 2, and I can solve for k by substituting a equals to negative 4 and h equals to 3 over 2 to get k equals to 10. And this is exactly the same result that we got from completing the square. You might find this method a little more reliable than the completing the square method. Exercise 2. Express this polynomial 2x cubed minus 5x squared minus 28x plus 13 in the form bracket x plus 3 close bracket ax squared plus bx plus c close bracket plus r. Pause the video here and give this question a good try. Now, one way to approach this question is to recognize that this is exactly what we've been doing in part 2 using long division. So if we run through the long division algorithm, like so, we are going to get a quotient of 2x squared minus 11x plus 5 and a remainder of negative 2. And since we know that the dividend is equals to the divisor x plus 3 multiplied by the quotient plus the remainder, we can solve this and we'll get a equals to 2, b equals to negative 11, c equals to 5, and r equals to negative 2. So this is one method. Alternatively, we can treat this as a polynomial identity. So we set up the two expressions to be equivalent to one another, and we expand the right-hand side. So this is a bit cumbersome. We'll get these terms. Then we compare. So we compare the coefficients of x cubed. A will be equals to 2. We can compare the coefficients of x squared. So 3a plus b equals to negative 5. Since we know that a equals to 2, b has to be negative 11. We can do the same thing for c and the same thing for r, and we get exactly the same result as method 1. So the first question I would like to ask you is, which method do you prefer? Do you think comparison of coefficients is faster, or by the long division method? Now I expect the answer to be quite mixed between the two methods, but however, if I change the question into this, find the remainder when 2x cubed minus 5x squared minus 28x plus 13 is divided by x plus 3. Now what happens is that the question has changed into just finding r. I no longer care about the quotient term. So would long division still be faster, or would the comparing coefficient method be faster? Well, it turns out that the polynomial identity method is a little bit faster, and here is why. If I equate them as a polynomial identity, it turns out that I don't have to expand and find a, b, c anymore either. Since it's a polynomial identity, I can substitute any number I like for x, and I'm going to choose a very nice number. I'm going to choose x equals to negative 3, because when I substitute it into the right-hand side, negative 3 plus 3, you'll see cancels out. Then I'll have 0 multiplied by ax squared plus bx plus c, and all of a sudden, a, b, c will vanish. All I'll get is r equals to this entire polynomial with the x replaced by negative 3. So r will be negative 2. So you see that if I just want to find r, this method is a whole lot faster when I treat it as a polynomial identity. And this brings us to the remainder theorem. So the remainder theorem states that if I want to find a remainder when I divide a polynomial by a linear divisor, and the linear divisor is ax plus b, the quick and easy way is not by long division, but just by substituting what makes the divisor 0. So by substituting that value in, so negative b over a, I will get the remainder instantaneously. So this is the remainder theorem. So let's now apply this remainder theorem in exercise 3, taken from the O-Level 2020 paper 1, question 8a. This is the A-Maths paper. So the remainder when x cubed plus ax, where a is some constant, is divided by x minus 2 is the same as the remainder when it is divided by x plus 1. Find the value of a. Pause the video here and give this question a good try. Let's go through the answer. So first we set the polynomial px to be equals to x cubed plus ax. So to find the remainder when divided by x minus 2, we need to substitute what makes x minus 2 0. What makes the divisor 0? So x has to be 2. We'll substitute x equals to 2, so p2 equals to 2 cubed plus 2a. Next, we want the remainder when it's divided by x plus 1. So what makes x plus 1 equals to 0? Well, x equals to -1. So we're going to substitute -1 inside, and we're going to get -1 cubed, which is still -1, minus a. And since we are told that both remainders are the same, so we can equate the two expressions together. And by solving this, we get a equals to -3, and that's our final answer. Exercise 4. The polynomial x cubed plus ax squared plus bx minus 7 has a remainder of 13 when divided by x plus 2 and a remainder of 23 when divided by x minus 3. Find the value of a and b. Pause the video here and give this question a good try. So once again, we'll start by defining the polynomial function px to be equals to the polynomial that we're given, x cubed plus ax squared plus bx minus 7. So now we see that we get a remainder of 13 when divided by x plus 2. So we're going to substitute what makes x plus 2 0. We're going to substitute -2. So p of -2 gives us a remainder of 13. So when we sub that in, we can simplify it and get 2a minus b equals to 14. We're going to call this equation 1. Next, since we get a remainder of 23 when divided by x minus 3, this means that p of 3 equals to 23. So when I substitute 3 into the polynomial function, I'm going to get and simplify it into 3a plus b equals to 1. So I'm going to call this equation 2. So we have two equations with two unknowns. I can solve the simultaneous equation by adding them together. The b's will cancel out. I will get 5a equals to 15. So a will be 3 and b will be -8. And that's my final answer. Here's something a little bit more challenging. Exercise 5. Find an expression for the remainder when the polynomial x to the power of 11 minus 678x minus 770 is divided by a quadratic divisor x squared minus x minus 2. Pause the video here and give this question a good try. Okay, let's go through the answer. Firstly, I hope nobody did the long division method because this will be very painful, very tedious if you're going to go through 22 lines of long division. So is there a better method? Well, we can first see the polynomial identity that the dividend is equal to the divisor times the quotient plus the remainder. So for the first thing we need to recognize is that the remainder isn't just some number. Because the divisor is a quadratic, the remainder is 1 degree lower than the quadratic, so it's going to be a linear remainder. That's why the question also hinted that it's going to be an expression, not just some number. The quotient is a degree 9 polynomial, but we don't really care about it. So how can we find ax plus b is the problem. Well, the divisor is factorizable. We'll get x minus 2 times x plus 1. And what we're going to do is we're going to do the remainder theorem twice. We're going to substitute x equals to 2, and we're going to substitute x equals to -1, because in these two cases, the qx will vanish. And we're going to form simultaneous equations. So that's the big idea. So let's begin. Let's substitute x equals to 2. Well, for the remainder, it will be 2a plus b. And if we substitute x equals to 2 in the degree 11 polynomial, we're going to get something that looks horrible, but it turns out to be just -78. So we'll call this equation 1. 2a plus b equals to -78. Next, we substitute x equals to -1. The remainder will be just -a plus b. And when we substitute -1 into the polynomial, we are going to get -93. And that is equation number 2. So if we take equation 1 and subtract equation 2, very simply, 2a minus -a will give us 3a. The b's cancel out. And we'll get positive 15 for the constant. So a will be equals to 5. And substituting that back in, we can find that b equals to -88. This tells us that the remainder is ax plus b, which is 5x minus 88. And that is our final answer. So now is your time to practice. So you can go to the info section below. You will see a link to my website where I've developed a applet that will randomly generate questions on remainder theorem. So do give it a try, and you can also check out the solutions inside it. So before we end, let's reflect on the success criteria that we've set out at the start of the lesson. Are you now able to solve for unknowns in a polynomial identity? And are you able to apply the remainder theorem? So if you have any questions on these two success criteria, you can post your questions down in the comment section below. With that, we have come to the end of part 3 on remainder theorem and polynomial identities. Do stay tuned for part 4, where we'll be looking at the factor theorem and how we will use that to solve cubic equations. Thank you and have a good day of learning.